Alright, hi Year 12s, this is Mr. Lim here, and this is our second video of WACE exams going through the 2018 one. Alright, so 2018, here we go. This is an ester. How do you tell? Well, look, there's an ester group right there. So, notice the high average, don't get this wrong. Okay, so we should be able to work out which one's the R and the R dash group. Hopefully you remember that this is the R dash group, this is the R group, and the R group comes from the carboxylic acid, and the R dash group comes from the alcohol. Okay, so therefore the R group from the carboxylic acid has 1, 2, 3, 1, 2, 3, 4 carbons. Okay, so this is butanoic acid, and the alcohol has how many carbons? 1, 2, 3, 4, 5. 5 carbons, so it's a pentanol. Except you also need to know where it is. It's a 1-pentanol. Of course, it doesn't actually ask you. It just asks what type it is. It's pentanol and butanoic acid, so we can know that it's not this one, it's not this one, it's either this one or this one. All right, and its name is going to be pentyl butanoate, which is this one, which is A. So that's the one it is, A. Okay, cool. So let's move on. Number 11, which of the following molecules is capable of demonstrating cis-trans isomerism? Okay, so what you've really got to look for is where's the double bond. And so if you look carefully, if you think about the structure here, the double bond here is in that first two. That's where the first double bond is. Okay, so you're looking for the thing that has only two extra bonds out of the double bond. All right, so therefore you find the double bond in each of them. Here's another double bond. Here, where's the other double bond? Here's the other double bond in this one, and where's the other double bond there? It looks like that one doesn't have a double bond, so therefore that can't have cis-trans isomerism. All right. Which one's the odd one out? The one in the middle. What you should recognize is that if the double bond is on a terminal carbon, and the terminal carbon has either 2 H's or 2 Brs on it, as both of those substances do, it can't have geometric isomerism, because as soon as you have two things on the same side of the double bond that are identical, you can't have geometric isomerism. The one in the middle, B, you can have geometric isomerism, and it will look like this with a H there and a H there, a H3C and a CH3 right there, cis or trans butene. All right, so just have a look when you're working out cis-trans isomerism. Work out where the double bond is, draw it out if you have to, and then you can work out whether it'll have cis-trans isomerism. All right. Okay. You'll notice that there were only 2 multiple choice questions on that one there, so just note that you don't always have the same amount of topics in the multiple choice. But anyway, this is aldehydes and their chemical properties. Okay, so name 2 reagents that can be used to synthesize C from B in step 3. So here is step B, here is C, here is B. How do you turn B to C, or synthesize C from B? Okay, so what have you got? You've got a aldehyde turning into a carboxylic acid. What reaction does that? It's an oxidation. So what are 2 things that can oxidize? I would suggest acidified. And remember, it's got to be acidified. You lose a mark if you don't get it. Permanganate or manganate, or acidified dichromate. Now, I remember the debate with teachers about, you got to name these 2 things. I think they were a little bit nice and they allowed chemical formulas, but if it does say to name it, please make sure you are giving the name of the reagent, not just the chemical formula. All right, so really read the question. Okay, next, write the balanced half equation to show B reacting to form C, and this was just a pain in the butt because this one, you just draw the you got to draw the benzene. You got to draw the benzene ring, and this HC3 with the CHO. turning into the carboxylic acid. Okay, with the H3C. All right. And so what have you got to do? You've got to add a water onto this side. You got to add 2 hydrogens on this side, and then you got to add 2 electrons on that side, and then you can draw an arrow going from there to there. I don't think it required any states, but what they did say in the marker's note is that a lot of kids just wrote a full equation. All right, full equation with the potassium permanganate or something else like that. Only write a half equation if they're asking you for a half equation. Make sure you read the question. All right. Also take note that don't just think that everything that makes a carboxylic acid has 4 hydrogens. Remember, it only has 4 hydrogen ions if it's going straight from an alcohol to a carboxylic acid. All right. Okay, physical properties. Read the question. That's what it says. Okay. Given that the molecular formulas indicate that the compounds contain the same number of carbon atoms but differ only in the number of hydrogen or oxygen atoms, propose a hypothesis for why there is a variation in the boiling points of these compounds. Okay, so this asks for a hypothesis. What did all the kids do? They just wrote an explanation. That one's got a high melting boiling point because of XYZ, of hydrogen bonding, so on and so forth. That one doesn't, right? You've got to propose a hypothesis. So hypothesis like if you increase the number of hydrogens and oxygens in the substance, it will have a higher melting and boiling point. All right, so like the higher the total number of hydrogen and oxygens combined, the higher the melting boiling point, something like that. Okay, you have to write a hypothesis. So the idea was that you picked out a boiling point as the dependent variable, an independent variable relating to the oxygens and the hydrogens, and then a relationship between them. Read the question. Okay. And now, and then those people who wrote like an explanation at that point got to the second question is like, oh, okay, now we have to explain something. Okay, and why now it's worth 6 marks, and you'll notice that it's asking for solubilities in water. All right, so it says responses to part B was quite disappointing. I don't know why this examiner took it so personally. Right, candidates were able to identify the intermolecular forces for butane, butanone, and 1-butanol, but some failed to mention the potential intermolecular forces for water. So remember, this is the solvent-solvent bonding. Okay, so you've got to talk about the solvent-solvent bonds breaking, the solute-solute bonds breaking, and the solvent-solute bonds forming. All right, so make sure that you discuss the solvent-solvent bonds. Candidates battled, such an emotive expression, to understand that due to the increased hydrogen bonding in the 1-butanol, there was greater solubility with water, and some did not consider energy requirements when discussing solubility. So the amount of energy required, so the amount of energy formed in bond forming should be greater or equal to the amount of energy required for bond breaking of the solute-solute and the solvent-solvent. Then the idea that alcohols will have more sites for hydrogen bonding than ketones, because ketones will also be able to hydrogen bond with water, but they will have lower solubility. The idea is that here's my ketone, and it can form 1-2 hydrogen bonds with water. Okay, so a H2O, H, yeah, there we go, and another H2O here. Okay, that's a ketone. A carboxylic acid, an alcohol, 1, 2, 3, 4, plus the hydrogen, can form 3 hydrogen bonds with water molecules. This one happens to be reversed, but then these two are the same. Okay, here's another water molecule. Okay, so because this one has 3 and this one only has 2, therefore it's going to have a greater solubility in water because it's producing more energy and therefore can dissolve better in the water. Look at this. Far too many candidates gave a like dissolves like response. They suck. All right, that's year 11. We are now in year 12. Got to do better than that. Many candidates discussed the predominant intermolecular forces rather than the sum of intermolecular forces. And so that's why I always harp on sum of intermolecular forces. So this is about dispersion, dipole, and hydrogen bonding. Okay, so make sure that you are discussing all 3. All right, so why does the alcohol, the butane, and the butanone? So simply butane will only produce dispersion forces with water, therefore they won't break the solvent hydrogen bonds between water, so therefore it won't dissolve very well. Butanol can produce hydrogen bonds which can produce enough energy to break solute and solvent bonds when the solute solvent bonds are formed. And butanone can still form all the same ones as the alcohol, but not as much because it can only form 2 hydrogen bonds compared to the 3 hydrogen bonds of the alcohol. All right. So next, again, look, this is the one that we did in our practical. It's make a chemical test to differentiate between these two things. Okay. Some candidates gave different reagents for the different substances. What idiots. Which means that they said, hey, okay, with this one, I'm going to test it with carboxylic acid. And the other one, I'm going to test with an alcohol. And you're like, but wait, that makes both of them the same thing. Yes, that's why it's wrong. Okay? You have to test them with the same thing. Right? Let's have a think. What kind of chemical test can you do to differentiate between a primary alcohol and a carboxylic acid? I would have just gone with the oxidizing agent, and remember, it has to be a self-indicating one, and it has to be an acidified. So something like acidified pot permanganate can do whatever, right? So KMnO4, KM begin O4, right? Observations. Okay, so remember, you've got to do the observations for whether it reacts or whether it doesn't react. So this one will go from purple to colorless, and obviously you might want to write it a little bit more. So a purple solution goes to a colorless solution, and you should recognize that the butanol, it would have to be in excess for that, right? And the butanoic acid will also have to be in excess, or you could just say a limited amount of acidified potassium permanganate, right? And then this one would go purple and stay purple. Well, less purple. Why would it go less purple? Because you're diluting it. But the general idea is that it's still going to stay purplish, and that one's going to go colorless. All right, that's the idea. For the molecular formula C6H12O, draw 2 different structural isomers, one which can be readily oxidized by acidified dichromate and one that cannot be oxidized. All right, show all atoms. Again, draw all atoms. This was done fairly well, so it's just a question of can you do this. All right, C6H12O, the C6H12 and the single O tells me that it's an aldehyde and a ketone, so you just draw aldehyde. And Mr. Lim's going to be lazy and not draw all of the atoms. And Mr. Lim would have not got full marks, but this isn't an exam. So that's an aldehyde which would have oxidized. And then you just draw a ketone. Because you can. Oops. Okay, and a ketone which would not oxidize. That's what you should do. Right. This one here. Now this one was a bit dicky because this one, the answer is C18H24I3N3O8. And when you solve this empirical formula, the O turned out to be 2.65 as the ratio. Right? Now 2.65 is close enough to 2.66, which is close enough to 2 2/3. Okay, so you should be looking on the lookout for all of the possible fractions. Okay, so you're looking for 0.5s, you're looking for 0.33s, you're looking for 0.66s, you're looking for 0.25s, you're looking for 0.75s, you're looking for 0.2s, 0.4s, 0.6s, 0.8s. All of those can be multiplied out depending on what it is. And so if you do get a 0.2, a 0.4, a 0.6, a 0.8, a 0.66, a 0.33, you know, go through your calculation again. Just make sure that you've done all the steps right. Make sure that you've saved the numbers in all your calculators right. And then be like, okay, whatevs. Multiply it out by 3, 4, or 5, or 2 as you need to, and then just see how you go. But like, if I got a 2.64, I wouldn't have rounded it to 2.5. I would have checked my calculation and just been like, okay, it's 2.645, which is close enough to 2.65, which is close enough to 2.66, which is close enough to saying that I need to multiply it by 3. Okay, but I would have definitely checked my calculation, which would have sucked. Anyway, draw leucine in low and high pHs. Okay, so put your charges in the right place And don't forget drawing all of your atoms. Now, I don't even remember what leucine is, but I'm just going to write an R in here because the main point is that you draw out in low pHs and high pHs. Okay, so I'm just going to draw the original form. Okay, and then I now can remember that, oh wait, this is a Zwitter ion in neutral. So now I got, okay, that's my Zwitter ion form, where it's that. Now, it's in low pH, which means there are lots of H3O pluses floating around, which means it's going to donate a proton to this Zwitter ion, and this is going to accept that proton. So therefore, you're going to draw something with that extra H there. So that is what you should have drawn, okay, in there. For the high pH one, again, here's your central carbon, your alpha carbon. High pH is basic, which means that it's going to donate all of its protons. Whoops, that's way too many C's. Okay, it's going to donate all its protons, and it's going to end up as NH and that minus. Okay, so make sure that your minus is over here, right? And your plus is over here, to make sure that your charges are in the right place. Make sure your charges are in the right place. Right, and then lastly, why is the structure of leucine pH dependent? Because it can act like an amphoteric substance, right? Which means it can accept and donate a proton. But what a lot of people missed out, they forgot to say that how it's going to be in neutral conditions. Okay, so can gain or lose protons, and in neutral conditions it's going to be in its Zwitter ion form. That's why its structure changes when it is in different pH conditions. All right, and that's it. We'll see how we go. Now I gotta go to class. Adios.